26. Okay. So this is in moles. This temperature has to be in Kelvin. And here's the reason why this has to be in Kelvin is because of the fact that if you look at this, if you work in Celsius, well, in Celsius, it's very, very easy to get a temperature of 0 in Celsius. Well, then you're multiplying 0 times all of this, and then that means either the pressure or the volume has to go to 0, which doesn't make any sense at all. Worse yet, you get a negative number, which means to make this thing balance out, you're either going to have negative pressure or negative volume, both of which can't happen. So,
watch me.
This is why we...
I just gotta fold. I just gotta turn myself inside out, and then I got negative volume. Gotta put my gallbladder on the outside. You got negative volume.
Okay. So this is already working Kelvin. No zeros, no negative numbers. Now let's talk about this value of R. So on your yellow sheet, over here on the back side, you have different values for R.
What? 1.0.
Okay. You've got 8. This is a universal gas constant, which is 8.31. And I always work with a 4, but your table, this just gives it as joules per mole Kelvin. So it's on the back of this yellow sheet. Don't memorize it. It's here. Okay. Personally, I go old school and I use 8.314. But anyway.
What letter do I want to put that in?
And there's actually different values of R depending upon which units it goes in. Like in chemistry, this is 0.0821 because that's liter atmospheres per mole Kelvin.
I'll put it under U.
And this is joules per mole Kelvin. So here's the reason why this works out. So I've got moles here. I've got joules per mole Kelvin. That way the moles cancel out, the Kelvins cancel out. I get joules, which balances out this side of the equation as well. So that way I get joules over here, I get joules over there. Life's good. Now, here's it's odd, but this is a situation where you all intuitively understand the gas laws. So let's say, for example, I'm going to come over here, and I've got a balloon in a vacuum. Okay? So, if you look at what's happening to create the shape of the balloon, so on an atomic level, what's happening for that balloon to have shape?
I know this one.
There's pressure. What's creating the pressure?
Can I answer any of these questions? Because I know all the answers.
Gas is doing what?
Moving.
Moving, and what are they doing when they hit the size of the container?
They're
They're bouncing off, right? They're creating a certain amount of force per unit of area, and that's creating pressure. Now, right now, is there pressure on the outside of the balloon as well?
Yes.
Yes.
That's always
Yes,
pressure, yeah.
right? Because inside the vacuum chamber right now, there's still air. So it isn't like it's a vacuum, you know, it's like, whoa, wow, there's air. Okay, so on the outside, you have all these little particles bouncing around and hitting the outside of the balloon as well. So here's what I'm going to do. I'm going to draw a vacuum. So what's going to happen to the volume of the balloon?
It's going to increase.
It's going to expand. Why?
Because there's only pressure on the inside. Because the pressure's coming out, but there's no pressure keeping it.
Yeah, so there's nothing to balance this out. So if I turn this on, okay? So, huh? Well, it's going to, otherwise it's going to suck down into the, hold on. Now, if I release this and equalize that pressure back out, then that's what happens. There's a hole down here. If you run it too long, then it sucks the balloon down into it, and that's bad. So this is a situation where kind of biology meets physics. In World War II, in the initial bombing rate, they used two main types of bombers: B-17s and B-24 Liberators, and B-25 Mitchells. But on those three planes, they weren't pressurized cabins. So, especially on the B-17s, they were flying B-24s, they were flying high altitude bombing rates over Germany. Well, as you go higher and higher and higher, what happens to your atmospheric pressure? It goes down, 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 right? So, with the bombing crews, they had to very much regulate their diet. And one of the things they forbid them from eating was beans. Why?
Because of the magical fruit. The more you eat, the more you toot. The more you toot, the better you feel. So let's have beans for every meal.
So imagine that you're on a bombing raid over Germany, right? And this is basically what's going to happen to your intestines because of the fact that you're under a very, very low pressure system.
No.
So, huh?
No, that's awful.
Well, I know.
That's how I never get a picture.
Yes, that's why they regulated their diet. Because otherwise, literally, they would just be doubled over in pain because of the fact that...
Oh, they wouldn't like explode or anything?
No, but no, it would be just very, very painful because of the fact that that gas inside was expanding just like this balloon was. And so they had to regulate their diet because you didn't want to be, being, strafed by, German fighters, and you're like, oh my God, okay? So that was one of the things that they did. So if you look at this, and there's all sorts of laws of gas laws. There's Boyle's law, Charles' law, Avogadro's law, the combined gas law, all this good stuff. So I'm going to show you this stuff.
Can I see Brooklyn for a quick interview, please?
For what?
1 minute, a quick interview.
Yes.
Brooklyn, boo.
What all things does she want?
See, like, that's like,
So much.
Okay. So here's how you basically work any gas law problem. Is that you've got P1, V1 equals NR T1. And then you can have, so this is your second set of conditions, P2, V2 equals NR T2. So here's the deal. So basically, what you look at is this. You have one set of conditions, then you have a final set of conditions. And usually 99% of the time, the number of moles is going to stay the constant because unless you're introducing more particles into the system or you have a leak, the number of moles is going to stay the same. R is going to stay the same because of the fact that it's a gas law constant. Hence the term a constant. It's not going to change, right? So if you isolate this and you divide this by T1 and you divide this by T2, so basically you have P1 V1 over T1 equals NR. And then you have P2 V2 over T2 also equals NR. So if this equals NR and that equals NR, guess what? They're the same. They're the same.
Oh my God.
So you get P1 V1 over T1 equals P2 V2 over T2. Now, let's look at what we just did. When I evacuated the chamber, do you think I changed the temperature of the system?
Probably not.
No. Okay, the temperatures remain constant. Okay, so if their temperatures remain constant, you have P1 V1 equals P2 V2. Oh, that's kind of cool. So initially, look what happened. I had a big pressure, right, and a relatively small volume. Well, once I created a vacuum, what happened to the pressure? The pressure went down, then to balance it out, that had to require bigger volume. Volume goes up. Easy peasy. Now, pressure and temperature, okay? So this is what happens, especially at this time of year. So you got P1 V1 over T1 equals P2 V2 over T2. So let's assume that your tire pressure, let's assume that the volume of your tires remains constant, which it basically does, okay? So let's say this is going to be a constant. So if you do a little cross multiplication, you get P1 T2 equals P2 temperature 1. So let's say it's a hot summer day, right? And on a hot summer day, you're going to have a big temperature, right? And you're also probably going to have a higher pressure. So why do you think you're going to have a higher pressure at a higher temperature?
Because everything's going like this.
Yes,
Going like
okay,
this.
Timmies are on Skittles, okay? Timmies have a lot of energy. Now, that's another thing that I don't want you to think too much about. Is that, wow, how do these particles have energy? Huh, wow, they speed up. Because kinetic energy, temperature is a measure of kinetic energy. So going, wow, they have a lot more energy. What does that mean? I don't know, okay? But we know that they have more energy, so it isn't like they have little like motors and it isn't like we press down on the gas pedal, wow, they have more energy. Okay, we're off, okay? But that's basically what happens. So if you look at what creates pressure, it's because of the fact that you have all of these particles colliding with a sensor. So it would be kind of like you can make the analogy with second graders. So let's say that you have the little ankle biters. Let's just go ankle biters. And so you're in a darkened room, okay, with second graders, which is a horrible thought. It just makes my skin crawl. But anyway, and so you're in a darkened room with second graders, and you're trying to get a feel for, okay, how much kinetic energy do these little vagrants have? So if you're not being hit very often in the legs by the little second graders, you're going, okay, hey, they're pretty calm today, right? Versus, wow, somebody, unbeknownst to you, throws like 10 bags of Skittles into the room. Wow, they're on steroids, and all of a sudden you're just being bombarded by these little second graders that are running into your legs. And, whoa, there's a lot more pressure. Therefore, they have a lot more energy, so something's given in that. In this case, it would be Skittles. So this is a situation where on a warm day, you have a high temperature and you have a high pressure, right? So look, what happens? Oh, it's cold outside. What happens to the temperature? Oh, you have a smaller temperature. Guess what? What happens to the pressure? Pressure becomes less. So this is why you're more likely in the wintertime to get a low pressure sensor on your light or on your car tire pressure because of the fact that the particles are moving slower because they don't have as much thermal energy to bebop around. Got this? So when you look at this in terms of this, okay, just go through and isolate whatever you're holding constant. So you're like, if your pressures are the same, okay, hey, then you're looking at volume and temperature, volume and temperature. If your temperatures are the same, P1 V1 equals P2 V2. If your volumes are the same, you got P1 over T1 equals P2 over T2. So if you get this, you can solve literally 99% of all problems involving gas laws, okay? And if you think of like little Timmies, that's the easiest way to visualize any gas loss situation. Like, oh, right, they have more energy. Oh, they're going to create more pressure. Oh, they have a higher temperature. Okay, got the idea. We're good. Okay. Now, I'm back here.
We're going on a trip in our favorite rocket ship, zooming through the skies. Blue Einsteins, come aboard. Get ready to explore. I can't see anything. There you go, now I can.
All right. What?
Oh, you didn't hear what he said.
No.
No.
Did I want to?
Since the principal.
No, I was singing with Joel.
All right. So let's say I want to strike the match. What am I going to have to do?
Rub it.
On the deal. Strike it.
Make energy.
Friction. Apply force over a. Because if I just apply a force, guess what?
Strike it.
It's not going to light. Fundamentally, right? Now, what if I push this very, very slowly?
What if it lit?
Not enough what?
Friction.
Not enough friction. Well, there's friction, right?
Not enough. Not fast enough.
Not fast enough. So
Not
what's
enough
the
energy.
speed going to do?
It's gonna create more friction faster, which a lot of friction gets. Okay,
Energy.
I'm just gonna be
Because
quiet.
fundamentally, what do I have to create?
Heat energy.
Heat
Thermal
energy, right? So I have to create enough energy to start to break the bonds, and what's known as activation energy. So activation energy is somewhat equivalent to like a roller coaster. So if I don't do this fast enough, it's like I don't get the reaction up to the top of the roller coaster. Okay? I get it part way, but it isn't enough to actually start the reaction. So if I go faster, let me go over here. Okay? I have made fire. Okay?
Prometheus.
And nice little thermal or exothermic reaction.
Burn the school down.
Come on, stay with it.
Burn yourself.
Burn the school down.
No, that would be bad. They frown on that.
No school. Yeah.
What happened? Burkamp blew up the physics lab.
I'll take one for the team.
Okay. All right. So
It didn't stay lit.
I'm going to take this piece of metal and I'm going to put it into the flame.
Oh shoot! It is.
What?
I still can't see it, so
It's visible. Oh wait, I can see it right at the tip.
Here,
It's blue.
somebody go to
It's blue.
Put your hand.
Put your hand in.
No, I mean, if you put your hand through it and you feel it.
Ooh.
Ready.
Now I see it.
Good fight. Now, anybody remember from chemistry, where's the hottest part of the flame?
Top of the blue cone.
The tip of the inner cone, right? Okay? So here's what I'm gonna do. Okay, now we need lights back on, because y'all have to see what's going on. Go. Okay, so this is actually two different strips of metal that are laminated together. So, I'm gonna put it in here.
It's bendy boy.
Now, what do you think happens to metal when it gets hot? Does it expand or contract?
Expands.
Expands. Now, different metals have different expansion rates. So, which metal do you think is expanding at a faster rate based upon a temperature change? The metal on the outside or the metal on the inside?
Outside.
Right? Because what's happening is that that's expanding faster and it's forcing that smaller one to curl in. So, as it cools, what's going to happen to this thing?
It's going to straighten back out.
Straight back out. So if you've got like, oh, that's really hot.
You almost put yourself.
If you look at like the old style thermostats that you might have in your house instead of the digital ones are completely different. But the old ones used to have like a deal where you would slide. And what happens is that inside your thermostat, there's a strip of metal like this. And so as your temperature in your house changed, it would change the pitch of this metal. And so you would have your thermostat set at a certain point. And so if you're talking about like in the summertime when it would get warm enough, if it would get warm, as the temperature warmed up, that metal would come up like this, and then the thermostat, then it would hit where your thermostat is set. That would complete a circuit, that would send a signal to your air conditioner to run. But then as the house cooled down, then you would change the pitch of this until it lost contact with that point, and then it would shut it off. Now the opposite happens in the wintertime. Your house cools down, oh, this thing straightens out, it reaches a point, boom, it kicks on the furnace runs until it warms up, it vents back out. So metals expand and contract at different rates depending upon the type of metal. Now, let's say for example, I'm going to take this piece of metal, I'm going to put this in here and I'm going to warm it up. So I'm going to take this and you'll see that it'll fit in here. And it's also machined to fit just inside of that gap. So here's what I'm going to do. I'm going to take this one first, and we're going to warm it up. So as this warms up, do you think I'll be able to fit it inside that gap? No, because on an atomic level, what's happening? What's happening to all of these little Timmies?
Skittles.
Okay? Yeah, they're on Skittles, right? So they're on Skittle overload at this point.
Overdose on Skittles.
Yeah. And when they do that, they occupy more space. So on an atomic level, these little bits of matter, electrons, protons, neutrons, otherwise known as stuff, thank you very much.
You're welcome.
Yeah,
But then when you have them all together, it's stuff and things.
it is. So the stuff is occupying more space. And so now when I go to put that in there, now it won't fit because of the fact that that metal has expanded and now it won't fit within the scalp. Now, here's the next thing I'm going to do. I'm going to let this cool down a little bit. Okay? And you'll notice that it will fit inside that gap. Okay? Right there. So what I'm going to do is I'm going to heat this side up. So three things can happen to the size of that hole. It could either stay the exact same, it could get bigger, or it could get smaller. Those are your three options. Stays the same, which means this thing would fit, just be a snug little fit like this. Okay? I can get it in there, but it's a tight fit. Or I heat it up and it's going to collapse, or the hole is going to get bigger. Those are your three options. So what do you think is going to happen?
Collapses.
It's going to get smaller.
Going to get smaller. Why?
Because the metal's expanding, so it's going to contract the hole.
Metal.
That's going to fill in that. So I shouldn't be able, so afterwards I shouldn't be able to put that in.
Oui.
Okay. Everybody cool with that idea?
Yes.
Jacob?
I just have a gut feeling
What's your gut
tell
feeling?
you?
It's gonna stay the same.
It's gonna stay the same.
Yeah, that's my gut feeling.
Why?
Explain yourself.
Gut feeling.
Math. I mean,
Math.
I don't know. I can't explain it right now, but I bet if it works, I'll explain it.
All right, so we got this nice and hot, right? Okay.
Oh, I got it.
It actually got bigger.
It got bigger. I like when out.
It got bigger.
It got bigger.
Agree with everyone.
Everyone's stupid.
No.
I am too.
Okay. Now, what's the guiding light of all things with Mother Nature? Mother Nature is lazy, right? Mother Nature does what's easier. So what do you think it's easier for Mother Nature to do? To try and compress these atoms into a smaller and smaller space. So if you've ever tried to take a balloon, squeeze it in, okay, it's really, really hard to do. So imagine this. Imagine if that was actually, let's say we had taken the piece that we cut out, and we actually had that in there. In other words, if it was solid. In other words, we took the piece that was in there, and we put that piece there, and we heated it up, what would it do? It would expand from the middle out. Okay? So Mother Nature is basically saying, oh, that's still going to be easier. We're going to expand this thing from the center going out. So that's why when you heat that up, and you would think intuitively, oh, it's going to try to expand. But it's really, really difficult to make a circle smaller. It's much easier to make that circle get bigger because it's a path of least resistance. So this is what, a lot of times, like in the industrial world, you can take advantage of this, like really, really tight-fitting bearings. So what you can do is, so a bearing goes over a shaft and allows something to turn on that bearing. So what they'll do is they'll have a custom-fit bearing, and they'll get it hot, like in a vat of boiling oil, like you're cooking French fries, and they'll get that bearing really, really, really hot. And what they'll do is that when it's really, really hot, they will slide that over the shaft. They have to put this on. Then, when it cools, it will lock itself in place because of the fact that it's going to collapse and seal itself back around that fitting. Got it? Good? Grand? Okay. Back we go.
We're going on a trip in our favorite rocket ship, zooming through the skies. Blue Einsteins. Climb aboard. Get ready for the sport. There's no need to die. Blue Einsteins.
Glad we got that recording. I'm glad.
I am too.
Very cool. Very nice.
Leave the assignment, just
You guys probably skip ahead like 20 seconds.
It's the backpack. It's always the backpack. At least Jason isn't here. That would make it significantly worse to be walking back.
I think we have a lot of white papers, and it's all the tests,
What?
so I'll put it in my test, and I'm
There we go. Check out this math.
Check out the constants.
And subscribe to PewDiePie.
oh, they've been measured and measured and measured. I mean, especially Steve. So, okay. So,
I'm giving them all the constants.
okay. So this is
That way
going
they
to
can follow
become your
along.
friend. So let me explain what you need for tomorrow for the assignment for today. So what you have here, and it's a weird thing in terms of the equations. So what you have here is called the coefficient of linear expansion. And notice that it is weird because of the fact that it has an odd degree of Celsius to the -1. Okay? It's a weird unit. You would think, wow, that's just kind of weird. So here's the reason why this works. So down here below, and this isn't on your equation sheet, I will always give you these equations because it's where the AP exam expects you to know that things expand, but they never actually make you do the calculations. Well, without doing the calculations, it really doesn't make any sense. So there's two versions of this L and L naught. So basically what you have is L equals L naught times 1 plus delta T and, or alpha delta T. And this is also as delta L equals L naught alpha delta T. Now, and they're the same equation, because basically if you subtract this over, okay, and this is, and then you factor it out, you basically get the same equation. So if you distribute this, you get the exact same equation. So here's what's important. And this is actually the one that's a little bit easier to see. This is L naught. This is your initial length. The beauty of this equation is that it doesn't make any difference what units your initial length is in. This could be meters, kilometers, whatever, okay? Now, this is alpha. This is this unit of coefficient, or the coefficient of linear expansion. Here's going to be your change in temperature. Now, listen to me, listen to me, listen to me, very carefully.
Oh, so that's not fish.
Yeah, this is this is a completely different fish.
Okay, I'm gonna write that down.
Okay, this is a completely different fish.
Eight fish done.
This is not angular acceleration.
Yeah,
Okay?
that was not.
And this is not angular momentum.
Yeah, I was
Okay?
really confused
And
for a
this is not
second.
time. Okay?
But wait, oh, it's temperature.
Temperature.
This temperature. Now, here's what's important. This is change in temperature. Listen to me. This is change in temperature. So you only get a change in length if there is a change in temperature. Okay? That's it. You only get this applying if there is a change in temperature. It is not temperature. Listen to me. It is not the temperature. It is the change in temperature. Now, here's an interesting thing that happens. Let's say you're at 10 degrees Celsius. How many degrees Kelvin is that?
Yeah, 283.
283, because you add 273 to it, so that's 283 Kelvin. Let's say you warm it up to 20 degrees Celsius. Well, that becomes 293 Kelvin. So a 10-degree temperature change in Celsius is the exact same as a 10-degree temperature change in Kelvin. Okay? That's another cool thing because you're just adding 273 to it, so you don't have to worry about like Fahrenheit, which is like 9/5, and it just gets really weird. So this could either be a change in Kelvin or a change in Celsius because it's the exact same amount of quantity involved. It doesn't make any difference. But this is why this works. So let's say that your initial length is, I don't know, 10 meters. So you have a chunk of steel 10 meters long. So then you'd go through and you would find the coefficient of linear expansion for steel, which is 12 times 10 to the negative 6 Celsius to the negative 1. And then let's say your change in temperature is, I don't know, 20 degrees Celsius. So here's why this is so cool, is that your Celsius cancels out and you're left with whatever units your L naught is in. So if your L naught is in meters, your change in length is in meters. If your L naught is in miles, your delta L is going to be in miles. So it's whatever this is whatever your units for L naught are. Okay? Okay. So we got that one. Now, you can also talk about area. So down below here, okay? Down below, you've got area equals area naught times 1 plus 2 alpha delta T, and if it's change in volume, V naught equals 1 plus 3 alpha.
That's volume, not velocity.
So,
Is
why do you think in area, why do you think there's a 2 there? Because it's going to expand in 2 dimensions. If it's volume, you have 3 because it's going to expand in 3 dimensions. Okay? So they all have the exact same format. 1 plus 2 alpha delta T, 1 plus 3 alpha delta T. So again, I don't care what units these are in. Okay? It doesn't make any difference. Just be consistent. Right? It literally, it's whatever units this is,
No units?
and whatever units this is going to be. Now, here's where you have to be a little bit careful. So this might be, I don't know, 1,000 cubic centimeters, whatever it is. So if the question asks for what's the change in volume, what you would do is you would plug this in and you would find the new volume But if it asks for the change in volume, you'd have to take this number minus that initial number. So you have to be careful with these thermal expansion problems. Are they asking for the new volume or are they asking for the change? So that's one thing that you have to watch out for. Okay, so let me stop that for a second.
Bye bye, everyone. Love you all.